A subcover of cover U alpha. So we take subcover from a cover U alpha is a subcollection. It is contained in U alpha. Subcollection of U alpha that covers S. That covers S. So it covers S actually. So then we say -1 comma 0.5 and 0.2 comma 1.2. So these two intervals are contained in the cover, but still they covers the entire interval 0 1. So still they cover the entire interval 0 1. So it is called the subcover. So these are subcover because we this is contained in the cover, and these are subcollection of a U alpha, and these both also cover. If we take their union, these satisfy all the condition of cover, but these are actually contained in a cover, so these are subcover. Okay, let's define finite subcover, and then we will move toward the complete metric. So let's define finite subcover. Finite subcover. So basically these are, we have recently defined the cover which were u1, u2, u3. So if we have an interval, for example 0 comma 1, okay, this is equal to S. Then covers are like that. We can say, if we make it dotted, then this will be like that. So these are, if we put their value, then we say that 0 comma 1 by 2, 0 comma 1 by 2, 1 by 4 comma 3 by 4, 1 by 2 comma 1. So these are basically the cover infinite covers of this interval, because after taking their union we will see that this S, these cover all the condition of covers. Okay, so but these are infinite number of sets that together cover 0 comma 1. 0 comma 1. So they together cover 0 comma 1. But if we take any three or any two of them that satisfy all the condition of cover, then these are called finite subcover. So finite subcover we can take, finite cover we can take like that. Zero comma 1 by 2 and 1 by 2 comma 1. So if we take if we check them, if we check the conditions of cover, what are conditions of cover? That these are U alphas, and each U alpha is open set. These are open set, and the union of these contains S or not? Yes, these contain S. So this means that these are finite subcover. Let's discuss about the complete metric. Complete metric. Let's discuss about it. So a metric space is called complete. A metric space is called complete metric if what to do, why it is called complete metric? If every Cauchy sequence so if every Cauchy sequence in that metric X, in metric X, if every Cauchy sequence in that metric X converges to point in X, is it means that if a sequence is Cauchy, and if a metric space has all Cauchy sequences, and those Cauchy sequences converges to a point that is contained in the metric space X, then that is called the complete metric. To show complete, if we just show that sequence is convergent, then we know that every convergent sequence is Cauchy by a theorem. So if we prove a sequence, if we want to prove that sequence is complete, then we have to just prove that it is convergent. If it is convergent, then every convergent sequence is Cauchy, we know from a theorem. So we don't need to prove it Cauchy again. Okay. So if we have a sequence of points in X, as when we apply limit and approaches to infinity at its nth term, if it approaches to X, that small x should contained in that small x should be an element, small x should be an element of capital X. So this should be an element of capital X set. Okay, I hope you have understand that definition. Now let's move toward the problem. So if we have an nth term of a sequence like that, for example, if we have xn equal to 1 minus 1 over 10 power n, basically this is the nth term of the sequence, and we have to check that it is complete or not. Then what to do? If we open that sequence, then we will get like that. We will get 0 0.9 comma 0 0.99 comma 0 0.999, so on. We will get that. Okay, so is the sequence, it is a basically sequence in metric space. So it is a sequence. If it is a sequence in metric space and we want to check that it is complete or not, then we have to check just one thing, that it is convergent or not. If it is convergent, then it is Cauchy, and then convergent plus Cauchy is complete. Okay, then we have to now show that it is convergent or not. Let's apply the limit on its nth term, n approaches to infinity, as n equal to limit n approaches to infinity 1 minus 10 power n. So if we apply the limit n approaches to infinity, this will be 1 minus 10 power infinity, this will be 1. So this means that this converges to 1, and that metric X is basically based on the real number that is contained in capital X, because this is a real number. So this means that this sequence 1 is complete sequence. Sorry, this means that this sequence xn equal to 1 minus 10 power n is complete. So it is proved now. Tomorrow we are going to discuss about a compact metric space. Compact, what means compact? Let's discuss tomorrow. Thank you very much for today's lecture.